Hello and welcome to our lesson on series and summation. So a mathematical series is just the sum of the terms of a sequence. So in our previous topic we talked about sequences, so we're going to start by looking at an example to connect that information to where we're headed with today's lesson. So suppose that a person has a starting salary of $50,000 and receives a $4,000 raise each year. Then the person's salaries over a 5-year period would be starting at 50,000 and then increasing by 4,000 each year, 54 in the second year, 58 in the third year, 62 in the fourth year, and 66 in the fifth year. And if this person were to continue working for this company and continue getting those raises, we can continue making that mathematical list, that sequence. So we talked about two things in our previous topic. One of them was defining an explicit formula, using an explicit formula to find any term on the list. So into this explicit formula, if I input a 1 for n, then I would end up with the first number on my list. So if I input a 1 for n, 4,000 times 1 would be 4,000 plus 46,000 would take me to 50, and there it is, the first number on my list. Input a 2, I get to 54,000. Input a 3, I get a sub 3. Input a 4, I get a sub 4, input of 5, I get a sub 5, and I can do that in any order, and I can find any number on the list. So if I wanted to find 10 years down the road, what would his salary be? I would plug a 10 in, and I can find that salary in that 10th year. So at the explicit formula, we can find any term on the list by plugging in that term number into the formula. Now we also have a recursively defined formula. With the recursive formula, basically, we have to know that to find a term, we have to know the previous term. So this says we can take any term on the list or find any term on the list by taking the previous term and adding 4,000. So if I wanted to know the 10th term, it wouldn't be possible unless I knew the 9th term, or wouldn't be possible to find it unless I knew the 9th term. If I wanted to know the 6th term, I could do that because I, on my list, have the 5th term. So finding any term requires knowing the previous term, but to get it, I would just take that previous term and add 4,000. Okay? So those are the two concepts from the previous topic. Now, the third concept, the third thing we want to be able to sort of navigate with our sequences is a series. And that is, again, the sum of the terms of the sequence. So instead of just wanting to know what his salary, he or she or this person's salary would be in any particular year, what if I wanted to know how much money this person had accumulated in terms of salaries over the course of, let's say, these first 5 years? Well, then I would want to add those terms together. So we would say the sum for the 5 terms using S sub 5 as notation would be the 50, 54, 58, 62, and 66,000 all added together. So that sum for those 5 terms, the total amount of money this person has made over the 5 years working for this place, is $290,000. Okay? So that's the concept. We have explicit formulas to find any terms. We have recursive formulas to find terms based on previous terms. And now the series, the sum of those terms on that list. Now, it was a relatively simple sum, adding up 5 terms, not too big of a deal. But some of our sums get a little lengthy, and sometimes just writing them can be lengthy. So we have notation to simplify things, and then we will talk about some properties and rules to shortcut some of our work. Okay? So first, let's talk about the summation notation. We use the Greek capital letter sigma to represent a sum. It's kind of a tough one to draw. I usually just kind of make it look like a squared E here, but this is really what our symbol should look like. It should have like a little tail here and a little tail here, but I don't generally draw those just because it's not fast, okay? But that is the Greek capital letter sigma, and it is used again to represent a sum. So we're going to see sums in two forms because we have two different types of sequences. We have sequences that are finite or countable. We have sequences that are infinite or uncountable. So we have a summation notation for each version. And you might be wondering to yourself, how do I find the sum of a list of numbers that goes on forever? Well, that will be possible in certain cases. We'll cross that bridge when we get to it. Okay? So for now, if we're looking at a finite series, the sum of the n terms in that sequence would be the first term plus the second term plus the third term plus dot 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 the nth term. So if I'm looking for the sum of 5 terms, I go all the way up to a sub 5, right? That would be the expanded version of that sum. So the summation notation says with this sigma that we're reading that sigma as find the sum of. In this case, it's the terms created by this sequence. So we have a sub I there, and I is going to be replaced with inputs, and this is telling me what those inputs are going to be. So it says start at an input of 1 and end at an input of n, and that's exactly what we're doing here. Start at an input of 1, end at an input of n. Okay, so this is find the sum. These are both saying the same thing. So what we have here is saying the same thing that we have here. Find the sum of n terms, right, where this is the function that's creating those terms, and we want to start from the first term and end at the nth term. That's what these two pieces are saying. Okay, find the sum of n terms created by the function that we're calling a. And I don't know if I did that justice explaining it, but if it's an infinite series, then instead of stopping at some term number, we go forever toward infinity. Okay? Now, I think once I put some actual values in here, this will make a little bit more sense. But the key things, we have this a sub I here. I sometimes actually we use j or k as well, but we call that the index of summation. But that I basically will always be replaced with this number up to this number. So if we have a 1 here and then let's say a 7 here, then it's going to be 7 numbers on the list. 1, 2, 3, 4, 5, 6, and 7 would be the inputs into our function. Okay, so we have this index here, but that index will always be replaced with 1 through n, basically. Alright, and I hope that makes sense. And we're going to look at some examples to make this a little bit more concrete. Okay, so let's try writing out terms and then evaluating if that's going to be possible. And I meant to put I here. So I represents the index of summation. And technically, this represents the lower limit, this represents the upper limit, but it's telling us where to start our list and where to end it. Okay, so if it has an end. If it doesn't, then we see an infinity up there. So just to wrap your brain around this again, make this a little more concrete, if I said to find the sum of the terms starting with k equals 3, ending with k equals 6 of a sub k, okay? Again, you have to understand this is where we start, this is where we end, and we want all the natural numbers are our inputs, right? So all the natural numbers in between. But basically, k gets replaced with all the natural numbers from 3 to 6. So if I was to expand this out, right, this is the notation that shortens it up. This is the expanded sum. How would that expanded sum look? So it would be, this is equal to a sub, not k, but 3, right, plus, after 3 would be 4, so a sub 4, plus, after 4 would be 5, so a sub 5, plus, after 5 would be 6, so a sub 6. So we're going to start at 3, end at 6, make sure we get all the natural numbers from 3 to 6, replacing k each time, and that's it. That would be the expanded form for this sum. Now we don't have any actual values or anything to evaluate or compute here because a is just a generic function. Once we have some actual functions and values to plug in, then we would take an extra step, and that's what will happen in this next one. Okay? So we want to find the sum of 6 terms. So we're starting at the first term, ending at the 6th term. So plugging in a 1, 2, 3, 4, 5, and 6 for I. So let's expand this out. We're finding the sum for 6 terms. The first term is 2 to the first power plus 1, because it says here start at an I value of 1. And then we're going to add the second term. That would be 2 times 2 plus 1, or 2 times 2, 2 to the second plus 1. And then the third term, 2 to the third plus 1. And then the fourth term, 2 to the fourth plus 1. And maybe I should have written a little smaller. Or maybe I'll just move this down here. Convenient. The fifth term, 2 to the fifth plus 1, and then the sixth term, 2 to the sixth plus 1. So that's the expanded form of the sum, and now we can actually just figure out what each of these things is and evaluate. Since we have no variables left in this situation, we can actually find this value. So 2 to the first is 2 plus 1 makes 3. 2 squared is 4. 4 plus 1 is 5. 2 cubed is 8. 8 plus 1 makes 9. 2 to the fourth is 16, and 16 plus 1 makes 17. 2 to the fifth is 32, plus 1 makes 33. And then 2 to the sixth would be 64. 64 plus 1 would be 65. And then I don't necessarily trust my ability to compute right now, so I'm going to go ahead and put this in the calculator. 3 plus 5 plus 9 and 17 and 33 and 65 and 132 is our sum. So this is going to be equal to 132. Okay, so we have this summation notation, which is the condensed form of our sum. We expand it out by replacing I or J or K or whatever letter is used there as our index of summation, by replacing that with all the natural numbers, starting with the lower limit and ending with the upper limit, and then evaluate if there are actual function values to plug in and add and get a value for. Okay, so 132 on that one. The condensed form, the expanded form, and then the value of the sum. Alright, so let's try this again. Number 3 says find the sum, and our function is 6x sub j minus 2, and then it gives us some definitions for x sub 1, x sub 2, and x sub 3. The first thing we want to do is just expand this sum out by replacing our index of summation with all of the natural numbers from 1 to 3. So this is going to be 3 different terms here. So the first term would be 6x sub 1 minus 2, plus the second term would be 6 times x sub 2 minus 2, plus the third term would be 6x sub 3 minus 2. So each term, again, replacing j with 1 through 3. So 1, then 2, then 3. And if we didn't have this information, we would have to stop here. But because it gives us values for x sub 1, x sub 2, and x sub 3, we're going to go ahead and replace those. So this becomes 6 times x sub 1 is given to us as 2 minus 2. Plus here we have 6 times x sub 2, which is 4 minus 2. Plus here 6 times x sub 3 is 6 minus 2. So 6 times 2 is 12, and 12 minus 2 makes 10 here. 6 times 4 is 24. 24 minus 2 is 22 here. And then 6 times 6 is 36. 36 minus 2 makes 34 here. So it's be 32, and 32 plus 34 makes 66, and it's late, and again, I just don't trust my computer right now. And when I say computer, I mean my brain. Okay, so yeah, 66. Yay, I can still add. So this ends up being a sum of 66. Okay, so we have again the condensed summation notation. We have like the expansion of the sum, and this would be the actual value for that sum. Alright, one more before I introduce another concept, or actually the rules and properties that might help us shortcut some of this work. If you feel like you can handle this, I would say this would be a good place to pause the video and try it. Otherwise, let's continue here. So here, we're finding a sum. We have a bunch of things defined. Let's deal with those in just a second. We want to expand this out first. So it's f of x sub I multiplied by a delta x. The first thing we want to do again is expand this out by replacing I with all the natural numbers from 1 to 4. So if I expand this out, first term would be f of x sub 1 times delta x, plus the second term would be f of x sub 2 times delta x. Third term would be f of x sub 3 times delta x. And the fourth term is f of x sub 4 times delta x. So just rewriting this 4 times, replacing I with everything from 1 to 4. Okay? And now we can do a little bit of evaluating because it gives me a whole bunch of information here. So we have f of x equal to x squared, but I'm going to deal with that in a minute. Now, or my next step, I'm going to replace x sub 1 with what it's equal to, replace x sub 2 with what it's equal to, replace x sub 3 with what it's equal to, and replace x sub 4 with what it's equal to. So I'm going to input the 0, 2, 4, and 6, and then I'll take the next step from there. So that's still my highlighter. How about a pen? Okay, so this will be f of x sub 1 is 0 multiplied by delta x, plus this will be f of x sub 2 is 2 multiplied by delta x, f of x sub 3 is 4 multiplied by delta x, and then f of x sub 4 it says is 6 multiplied by delta x. Okay? Now, the next step, I'm going to do two things at once. F of 0 I know how to find. That means input a 0 into f of x, which is x squared. And also I'm given down here at the end, I'm sorry for the zooming, but delta x is equal to 2. So I'm going to input 0, 2, 4, and 6 into my function, and then each of those function values gets multiplied by my delta x, which is 2. Okay? So lots of highlights, but I think you see where I'm going. So f of 0, again, 0 going into f of x, it's going to be 0 squared. Well, 0 squared is, oh, my eraser is too big. Sorry, 0 squared is going to be 0, and that's going to be multiplied by delta x, which is given to me as 2. Plus f of 2 would be 2 squared, which is 4, multiplied by delta x, again, is 2. F of 4, 4 squared makes 16, multiplied by delta x, which is 2. And f of 6 would be 6 squared, or 36, multiplied by delta x, which is 2. So this one is 0. 4 times 2 is 8. 16 times 2 is 32. And 36 times 2 is 72. So that looks like 102. Let me just not take any risks. So sad. And 8 and 32, 100 and... Oh yeah, see? This is why I use the calculator, because I missed a whole 10 in there. It's fine. Alright, so 8 plus 32 plus 72 makes 112 for our sum. So we're going to say that this equals 112. So again, three sort of components here. We have the summation notation, we have the expanded form of that sum, and then the actual value for our sum. Okay? Now, this work, while not difficult, especially if you have a calculator when your computer doesn't work, can be shortcutted. I don't know if that's a word. Sometimes we can take some shortcuts because we have some properties based on patterns and things that help us simplify some of our work. So we have some summation properties here. These properties will make a little sense when we see them, but the first one says, if you're finding the sum, right? Come on, Heather. The sum of a list of numbers starting from 1 to n as your natural number inputs of c, where c is a constant, that means you're making this list however long you want the list to be, but every number on the list is the same number. So if you add all those up n times, then n times c ends up being the sum for all of those constants, okay? So if it's the sum of a sequence where every single number in that sequence is the same constant, just multiply the constant by n, how many times you have it on that list. Right? If it's some constant times a sub I, which is defined for us as a sequence, then we can find the sum of the list of numbers in the sequence and then multiply by the constant, so we can separate that multiplication out. So we can see here the product here, we can take that out in front of the sum. And then if we have the sum of two sequences here, if we're trying to find the sum of the sum, we can separate those two individual sums. And if we're trying to find the sum of a difference, we can separate those two sums again. So here we're separating, and then here we're separating. Okay? And over here, some summation rules, different from properties. This just allows us to sort of rewrite some things. These rules actually help us to evaluate. So if I'm finding the sum of a sequence defined by I, then my inputs going from 1 to n are going to be the same as my outputs. This would be like a y equals x situation. So the first number on the list is 1, the second number is 2, the third number is 3, and the last number is n. So inputting 1 through n gets the same exact outputs. So this formula here provides us a way to shortcut, right, the actual sum. So I don't have to list all the numbers out and add them. I can just plug n in here. I can plug n plus 1 here, divide by 2. That's going to get me the value for that sum. And then we have formulas for also I squared, which would be like an x squared, and then for I cubed, which would be like y equals x cubed. So if we think about these, now these are continuous functions, obviously, but the same sort of concept, okay? So if we have linear, quadratic, and cubic functions there, we have formulas that we can use to evaluate those sums. Alright, so let's try to apply some of these properties and rules. For instance, on number 5, we're trying to find the sum of 40 numbers, because we're starting at the first number and we're going up to the 40th number. That's 40 different numbers. But this is the only number that's 40 different terms in my sequence, but each of those terms is 5. So if I listed out 5 40 times and then added it together, I would have 45 times, or 5 40 times. Okay, so the very first property, and I'll try to highlight here to make some connections. Number 5 here, we're going to use this very first property that says if you're adding up a constant value n times, then it's just n times c to get your sum. So this is just going to be 40 multiplied by 5, and so our sum has a value of 200. Can't get much easier than that. Okay? Now number 2, we're going to use two different things here. So first, I can see that I have a function being multiplied by a constant. And so I'm going to separate this using my second property. This second property here, if I have a constant multiplied by my function, I can move that constant out in front of my sum. So I'm going to apply that here and rewrite this as 2 times the sum from I equals 1 to 22 of I. And now I can focus on finding the sum of these 22 terms. Now I actually don't have to list out those 22 terms and add those 22 terms up, because this is one of my formulas. So now I'm going to apply to this. Maybe that's a bad color. Let's try this color. Apply to, that is my pen. Goodness gracious. Let's try this. There we go. This, right, that's what I see here. I'm going to apply this formula. Okay? So what I'm going to do now is multiply 2 by the sum of the 22 numbers, okay, which I'm going to evaluate using that formula. So it's 2 times, I'm going to use brackets here. Top of the formula says n times n plus 1. So n is our upper limit, that's 22. That's going to be multiplied by n plus 1, which would be 23. And then that gets divided by 2. And that's it. It's just computational work from here, which is scary for the tired brain. I know the times 2 and divide 2 will cancel, so basically just the product of 22 and 23, which makes our sum 506. And so being able to use the formula much faster than having to list out those 22 terms and then add them together and then multiply by 2. Okay? So similarly here, this time I'm going to apply, again, two things. So first, let me use orange. I have a difference of two separate, functions, basically. So if I have a difference, then I can expand that out. So I'm going to separate that one difference into two differences here. The sum Instead of the sum of a difference, it's going to be the difference of two sums. So when I separate this out, it becomes the sum for 2i squared, which again I can separate that. That's a constant. So I'm going to make this 2, that's an ugly 2, 2 times the sum of I squared, and we're going from I equals 1 to 14. So that's this piece of it. Okay, I moved the 2 out and I kept the I squared in, and then I want to subtract the other piece of it. So that would be the sum from, again, I equals 1 to 14 of 3. Okay, so I separated that out. And now a couple things. This will be 2 times for... I'm going to run low on colors here. Let's pick another... Did I use pink? I feel like I did. No, I did not. But I don't like that pink. Okay, so 2 times I squared is another one I have a formula for. So that formula is here. And again, I squared. So n times n plus 1 times 2n plus 1 over 6. That's what the value of that sum is going to be. So this is fraction. I know the bottom of the fraction, that's easy. That's going to be 6. The top of the fraction, n times n plus 1 times 2n plus 1. So first, my n, again, that's my upper limit here. That's going to be 14. Times n plus 1, which would be 15. Times 2n plus 1. So 2 times 14 is 28, and 28 plus 1 makes 29. So that formula gets me the sum for all of those terms. And then I'm going to subtract the sum of, well, this will be a constant 3 added up 14 times. So that's applying that first one again, which I think I highlighted in yellow. Yep, so that's the yellow again. So I can just multiply 14 times 3 for that piece. And now I'm going to go to my calculator so I don't goof anything up. And I'm sorry if the scrolling is getting to you. Where's my calculator? Did I put my calculator away? It's not coming out to play. I must sorry, gonna get my family for a second. And I don't know why my calculator disappeared. Okay, so back on track. I got 2 times a fraction on the top, 14 times 15 times 29 on the bottom, divided by 6. And then from that, we want to subtract a product of 14 and 3, not less than, times 3. And I'm not sure if this is right. I don't think I need these parentheses, but make sure I typed it in there. And yep, looks good. 1,988. So our sum is 1,988. So imagine if we had to expand all those terms out, all 14 of those terms, and then put them together. Quite a large sum would be very tedious, but these properties and rules help us shortcut all of that. Alright, so last one. Again, I have a sum. I want to separate this out. What have I not used for highlighters? I used green, blue, pink, orange. Oh, I need another color. Let's go to custom. How about a light purple? Okay, so I have these sums. I want to separate, instead of the sum of a sum, right, I want to separate it into individual sums. And so this is going to go into 3 pieces. First, the sum from I equals 1 to 6 of I squared. So we'll use that formula we just used. Plus 3i here, I'm going to separate that twice, or that's going to be 3 times the sum from I equals 1 to 6 of I. So just pulling the constant out there. And then lastly, I have the sum from I equals 1 to 6 of the constant. Okay? So now things I've done already a couple of times. So I squared, that one was pink. We said this first one is going to be a fraction. and on the bottom was a 6. On the top was n, which is 6, n plus 1, which is 7, and then 2n plus 1. So 2 times 6 is 12, plus 1 makes 13. Plus, the second one is going to be 3 times I. Let me just go back up here. I is n times n plus 1 over 2. So n, which is 6, times n plus 1, which is 7, divided by 2. Plus, over here we've got a constant, so it's just going to be 6 times 5. That constant 6 times. And now an actual computer, because mine, yeah, you've already seen it. 6 times 7 times 13 in the numerator, 6 in the denominator, and then we're going to add to that 3 times another fraction, 6 times 7, which, I mean, I know it's 42, but just, I'm going to put it all in here to be safe, and then lastly 6 times 5, which again I know that's going to be 30, but I've come this far, why roll the dice? And I end up with 184, so that is the sum for that. Okay, that is the sum of that series. That's the sum of all the 6 terms in that sequence. Okay, so not terrible work. I'm sorry for all the scrolling. I hope you were able to see enough of that, or you at least have the notes in front of you. I didn't do a cubic example, but you might see one of those in your homework. Hopefully you've got enough to get you going, but as always, if you need some extra help, then reach out. Until next time, take care.